Good afternoon, everyone. Our next speaker is Professor Geetha Venkataraman, who is a professor of mathematics at Dr. B.R. Ambedkar University, Delhi. Professor Venkataraman has done her doctorate in mathematics from Oxford University in group theory. Today, she will be talking about the unreasonable effectiveness of mathematics. Let's welcome her for today's talk.
I hope you can all hear me. Yes? Okay. Thank you very much to the organizers for giving me this opportunity to be able to address all of you. And it's a pleasure to see so many young women sitting in the room. Today, my idea is to sort of tell you about why maths is so interesting. Okay, I think I may be selling it to people who already understand that, but nevertheless, the idea is that I tell you a bit about how many different ways in which we can, immerse ourselves in mathematics and different ways in which we can enjoy mathematics. Since this is a popular talk, I've kept the technical parts to most minimum, as minimum as I could. But given that it's a popular talk about mathematics, there will still be a little bit. Okay. Also feel free to interrupt and stop me and ask questions even while the talk is on, because the whole idea is for you to get a sense of what's happening and so on. Okay, so this is kind of in three parts. The first part I'm going to touch is symmetry. And you'll see this is written in a very curious way. This is called an ambigram. So if you rotate this by 180 degrees, it'll still look the same. Okay? So symmetry itself is portraying symmetry here. And of course, these are flowers. We'll see how we could possibly look at nature through symmetry. This kind of, it's a jali, window jali, which you'll find in old monuments. So if you go anywhere, you're going to find a window decoration like this, a jali like this. And this is usually what we in under symmetry call wallpaper patterns. I'll be telling you a little bit about wallpaper patterns. And can you see this? This is like butterflies just filling the plane. Okay? So this is an example of Escher's art. MC Escher, if you haven't heard of him before, you should go look him up. But again, I'll tell you a little bit about how he makes these things. And it's purely by, I mean, even you can do it in a way, once we figure out what the trick is. But these are lovely examples of wallpaper patterns. And then a bit about how mathematics and medicine come together. Most of you must be aware of what a CT scan is. I hope you've never experienced it. But you might not know, but its origins are from a theorem in real analysis. Okay. So often there is this divide in maths about, what is pure and what is applied. There is no such difference, right? And in fact, you'll realize that through this talk that many of what we see are applications are just coming out from what would have in the past been called pure abstract mathematics. Okay? So you do maths for math's sake, and then lots of it is useful, and a lot of it is just fun. And once you fall in love with mathematics, you don't fall out of love, unfortunately. Actually, that's good, isn't it? And I'm sure all of you would have experienced this thrill of having solved a problem. Yeah? And then the kind of high it gives you when you've solved a problem, and particularly one that you've been thinking about for some time. And that's what keeps you going, whether now I've spent like decades and decades doing mathematics. It's the one constant in my life, I would say. So All of this you'll realize is just coming out of something that has been done in maths, and later on people have realized, oh, they could use it to apply it to something else. Okay. Okay, so I'm going to give you, first of all, a very intuitive understanding of symmetry. And so a symmetry of a figure. So imagine, I mean, right now, let's just stick to things in our space, which is R cubed, right? All of you are familiar with the fact that our real space where we are living in, 3 coordinates are enough to define things. We'll call that R cubed. But of course, you can generalize it and you can talk about Rn. But if you have a figure which is, okay, so here's, just imagine that this is a rectangle, which is, so there's a, the way I'm holding it, there's a rectangular hole in the place where it is sitting, okay? Now a symmetry is an action that I can do on this. Imagine that there's no writing and stuff like that on it. Okay? So symmetry is an action that I can do on this, so that if you people close your eyes, and then I ask you to open it, and you think I haven't done anything. Okay. So close your eyes. Okay. Now open your eyes. You will see actually I've done something because this was pointed to that direction. But if it had been just a plain rectangular thing, then you would have not figured out that I did this. I rotated it by 180 degree about the center. So that's just the intuitive idea of what a symmetry is. Something that you can do to the object such that you're not allowed to tear the object and reconfigure it. What you can do to the entire object so that it comes back looking exactly like it did before the action was done. Okay, so that's what a symmetry is. Now the point is that once you define it in this way, but you still need to keep track of the actions you do. Right? So what do we actually do in terms of keeping track of the actions? I'll start with something very simple, which you're all aware of. So if you look at a square, okay, so what I've done here is there is this outline of the square I've drawn, A, B, C, D. And this is like a cutout that I have. And the question is that what are the things that I can do to the cutout so that it comes back in the same outline space. Okay? And then, so one of the things that you will pretty soon realize is you can do rotations and you can do reflections. That's all. Nothing else you will be able to do, which is a symmetry. And when you want to talk about a rotation, there are 3 things you have to keep in mind. One is the point about which you're going to rotate, the axis about which you're rotating, okay? And the direction in which you're rotating. So in this case, the rotations have been done about the center of the square, which is the place where the 2 diagonals meet. And the axis is perpendicular to the plane of the square. And I'm using the anti-clockwise direction. And you can see once I do a 90-degree rotation, I've marked the vertices of both the outline and the cutout in the same way. And you can see A has gone to B, B has gone to C, C has gone to D, D has gone to A. That's how you keep track. Okay? And then you have a 180-degree rotation, 270, and you'll be able to see that pretty much none of the other rotations will be symmetries. And similarly, if you think of folding your cutout so that both parts match exactly, then you'll realize that you're basically reflecting about a line. And you have a vertical, a horizontal, and 2 diagonal reflections, and these are the only reflections possible. There's another example on the screen, which is a equilateral triangle. I've done pretty much the same thing, but I've done a 90-degree rotation, and you can see that the 2 things don't match up. So you need to be able to keep track of your symmetries, and usually it doesn't matter that I'm taking something as nice as a square. It could be any piece of paper cut in a particular shape that you're looking at, and you just mark what you think are important points on that, and then you keep track. Similarly, you can do this for three-dimensional objects as well. Okay. So now we know intuitively what a symmetry is, and we know a way of keeping track of what these symmetries are, right? So let's look at a rectangle which is not a square, and you'll pretty much realize that there is what is called a 0-degree rotation. That's do nothing. You can't have, the 90-degree won't work, 180 will work, and then of course, those are the only two rotations you have. Again, the diagonal reflections won't work, but the vertical and the horizontal will work. So this is what you get. Just 4 symmetries are there for a rectangle which is not a square, whereas for a square we had 8 symmetries, 4 rotations and 4 reflections. Now what will happen if you take this cutout you have, either it's a square or a rectangle, and you do one action which is a symmetry, and then follow it up by another action which is also a symmetry? Then it will take that thing back exactly looking as it did before, right? So symmetry followed by a symmetry is again a symmetry. And therefore, you can create what is called a multiplication table, which is something like this. So this tells you that if you apply a R 180 degree first, followed by another 180 degree, you basically go back to the starting position. Or you do a horizontal reflection, and then you do a 180 degree rotation to that thing, you end up getting what would have happened when you applied a vertical. So this is sort of telling you that this applying a symmetry after a symmetry brings you back to a symmetry. So it's what's called closure. Okay. And indeed, if you want to look at symmetries more formally, so in our case, we're looking at sim x. So whatever your x is, x in our case here is a rectangle, but it could be this bottle, it could be a building, it could be anything in 3-dimensional space or even n-dimensional space. We'll come to that a little later. But right now, we are sticking to 2-dimensional things. But this, what I'm going to put down now, works for all of these. So sim x, x is going to be my object. Sim x is the collection of all its symmetries. So if x is the rectangle we looked at, it had 4 symmetries: 0-degree rotation, 180 degree rotation, horizontal reflection, and vertical reflection. And the table tells you that a symmetry followed by a symmetry is again a symmetry. So this thing is denoting that first you apply T and then S. And let's see what are the things that it will satisfy. So what happens is there's closure. Then you only know how to do 2 things, combine 2 things at a time. What happens if you have 3? If you apply without changing order, it doesn't matter how you put your brackets. You will get the same answer. That's associativity. And there's something called the identity element, which is your do nothing. So if you have a do nothing and then you apply a symmetry S, it's the same as just applying S. And it doesn't matter in which direction you do this. And for every symmetry, there is what is called the inverse of the symmetry. So if you have in the rectangle case, every symmetry is its own inverse. If you apply that twice, you'll get it. But in a square, if we have a 90-degree rotation, what would be its inverse? 270-degree rotation. So if you do a 90-degree rotation and then follow it up with a 270-degree rotation, you'll get to the original position. So the point though is that for every S, there is a T in the collection such that when you apply these one after the other, in whichever direction you get back to identity. These properties and this nice way of combining is called a group. Okay, this is a mathematical algebraic object called a group. Now, I don't know, many of you may have already done some group theory. How many of you have done any group theory at all? Only this thing. So it doesn't matter if you don't know what groups are. I've told you what they are. It's a closed system. And you know, the most familiar example of groups, which you've all done in school, is integers under addition. Right? If I take two integers and add them, I'll again get an integer. You would have learned, in fact, in middle school, you start learning these things that, oh, associativity holds, 0 is the additive identity, every element has a additive inverse, right? So the additive inverse of minus 100 is 100, and so on. Similarly, if you look at real numbers or rational numbers, non-zero ones, under multiplication, that also forms a group. But they're all groups where the order doesn't matter. Okay? They are called abelian groups because it doesn't matter whether you do S star T or T star S. But in these, it matters. The rectangle, it doesn't matter. But you go back to the square and you check it. If you pick two things, say a reflection and a non-180-degree rotation, then you'll find that they don't commute with each other. So those are called non-abelian groups. Anyway, the point I'm making is that you take any object X that you like, take its collection of symmetries, there is a nice structure to it, and that structure is called a group. And the more symmetrical your object is, the larger this group will be. So if you saw the group of symmetries of a rectangle, it had size 4. Whereas if you look at a square, it has size 8. Okay, so let's take triangles. Suppose I have a scalene triangle. That means all three sides are not equal. What do you think its symmetries will be? Only one symmetry, which is do nothing. Okay. If I take an isosceles triangle, which is not equilateral, then what do you think will happen? So isosceles triangle, there is this line of reflection, right? So there'll be one reflection and one rotation, which is the 0-degree rotation. And the equilateral, so if you again look at the triangles, the least symmetric was scalene. Its symmetry group is size 1. Then the isosceles triangle, which is not equilateral, its symmetry group is size 2. What do you think happens in an equilateral triangle? How many symmetries? 3 reflections and 3 rotations. Okay. So now give me the answer if I ask you if I have a regular pentagon, how many symmetries? So equilateral triangle, 3 reflections, 3 rotations. Square, 4 reflections, 4 rotations. So if I have a regular n-gon, 2n is the size of its group of symmetries. And in that, n of them are reflections and n of them are rotations. And you can make this multiplication table, which is really nice. You can actually do things and figure out things about that group. Okay. So coming back to this, so the groups measure symmetry. Okay. So this is again just an illustration of what happens if you first apply a horizontal thing, reflection, and then a 90-degree rotation, it ends up being a reflection. These are the inverses, which you already told me. Okay. But what is a group formally? Okay, so here's the little bit of maths that I've put in. But I think all of you will have a sense of this. So Rm, just m coordinates, entries are from real numbers. Okay? Non-empty set. That's cool. Bijective function, everybody understands. What do I mean when I say f preserves distance? So if I take 2 points in Rm, say x and y belonging to Rm, there's a distance between x and y. You've learned distance function in school, right? So if I had x as x1, x2 and y as y1, y2. Okay, so if this was my x and this is my y, this distance, what is the value? Under root of x1 minus y1 whole square plus x2 minus y2 whole square. So if you have m coordinates, you'll just have more of those differences squared coming in, right? So you know the formula for distance. So when we say, so this is the, say the distance between the point x bar and y bar. When we say that f is distance preserving, we mean that the distance between these 2 points and the distance between where f takes x bar and f takes y bar, that has to be the same. That's all distance preserving means. And this has to be for all x bar and y bar belong. That's why I said you can't tear and reassemble. That's essentially what it meant when I said that intuitively it's the action that you can do on the figure, bringing it back, looking exactly the same. Okay, so this is the formal definition of what this thing is. And in fact, there are things called metric spaces. These are generalizations of non-empty sets on which there is the concept of distance. Okay, pretty much like it follows the usual things that we think distance should satisfy. That is, the distance between you and me should be the same as the distance between me and you. So d of xy should be equal to d of yx. D of xy will be 0 only if x equals y. Then it should follow something called the triangle inequality. It's always greater than or equal to 0. So there are these rules by which you can define a distance function. And if you have a non-empty set with a distance function on it, so that makes it a metric space. So you can talk about groups of symmetry for subsets of metric spaces also. But this is the level at which we are not even going to go into this definition. For us, the intuitive one is more than enough. So for planar figures, that's that regular n-gon. We saw that n rotations and n reflections we have. This group is denoted as the dihedral group of degree n. Okay, that's the notation which has been this thing. And it has degree n because it's symmetries of the regular n-gon, and it has 2n elements. And as long as n is greater than or equal to 3, dn is non-abelian. The rectangle is sort of what is your d2. But it's not really, I mean, dn, basically we start looking at it from n greater than or equal to 3. That rectangle ka thing is also called a Klein's 4 group. Okay? But are these the only type of symmetries that you can have for planar figures? I mean, so there are rotations and there are reflections. Can you think of a figure which has only reflections? There's always a 0-degree rotation, but is it possible that it has isosceles triangle is there, 1 0-degree rotation and 1 reflection. But suppose a figure is it possible to have a figure with just a 0-degree rotation and 2 reflections? Is it possible to have a figure which has exactly 2 rotations? Exactly 3 rotations, exactly n rotations? What do you think? Circle is a fantastic figure, but the problem with a circle is it has infinitely many reflections and infinitely many rotations. Every diameter is a line of reflection, and so its symmetry group is infinite. So, but I'm asking something else. So can you think of a way in which you could create something which has exactly 3 rotations and nothing more? Yeah, okay, so that's exactly what I have in my next slide, possibly. Is this what you were sort of thinking of? So basically what's been done is you've taken an equilateral triangle and sort of modified it by putting these legs. So now what happens is your reflection lines are no longer reflection lines. So you can do this to anything. So you can do this to a square. So if you had a square to start off with, right? So I just you can add a width. That's all. Okay. And what you do when you do something like this is the reflections go away and only the rotations remain. Okay. So you can have planar figures which have just rotations and no reflections at all. But what is really amazing, and this is actually a result that you can prove, this one is when you try and spoil a line, basically a rectangle. So you do this and you do this. That's what this arrow is. Now, this is really remarkable. It turns out that if you have a finite planar figure, what that means is I can draw it on a piece of paper, or basically it can be drawn within a rectangle. Okay? That's what finite planar figure is. Okay? And for a finite planar figure, the only symmetries are rotations and reflections. You don't have anything else. And further, what's more important is that either they will always, if there are only finitely many symmetries, so the circle doesn't come in this, right? If you know that the object has only finitely many symmetries, then either they have to have an equal number of rotations and reflections or only rotations. So there is no figure, planar figure finite with only finitely many symmetries where you can have 2 reflections and 3 rotations. Not possible. Okay? And you can actually prove this once you develop the theory, group theory, and so on and so forth. So the most important takeaway here is that if you have a finite planar figure which has only finitely many symmetries, then either it has an equal number of reflections and rotations or only rotations. Okay? Now, what other things can we look at using symmetry? And this, okay. So this is called a strip pattern. So basically you choose any design you like. Think of this as your number line, and at every integer point you're stamping one of these. Okay? It's continuing infinitely to the left as well as to the right. Okay. Of course, you can still ask what are the lines of reflection, what are the points about which I can rotate. So for a strip pattern, what else is possible other than reflections and rotations? Is there something you can think of? Yeah, just vocalize what you're thinking of. Yeah, translation. So it's like I can tell Smiley march one place to the right. So everyone jumps one place to the right. It still looks exactly the same as it did. Okay? So there is always built in something called a translation for a strip pattern. Right? And so in general, I'm not talking about this strip pattern, but in general, these are the 4 types of symmetries you can have for strip patterns: reflection, rotation, translation, and there's something called a glide reflection. So what a glide reflection you can think of is, so if suppose you translate and then you reflect about a line which is parallel to the translation. Okay, so if I'm translating like this, in this direction, then my line of reflection also has to be parallel to it. And if I do a translation followed by this reflection, together the effect is called a glide reflection. Okay, that's pretty much what a glide reflection is. These are the 4 types of things that can happen, and these are also called the symmetries of a plane. So if you look at the plane as a whole, these are the things that you can do to the plane. And how do you keep track of it? You draw an R and see what is happening to the R, basically. Yes. Now, if we come to this particular strip pattern, what do you think will be the symmetries here? You can have this line of reflection between 2 smileys, right? If I reflect, it will still look the same. Or I can have another line which goes through the middle of the smiley. 180-degree rotation won't work because I'll get an upside down smiley if I do that. But if I had squares instead of smileys, then that's possible. And then, of course, translation. Okay? So the symmetry group for strip patterns will always be infinite, because t is just when you move 1 unit, then I can get t squared, t cubed, t to the 4, and so on. And similarly, if I go on the other direction, I can write it as t to the power minus 1, t to the power minus 2, and so on. So this powers of t, which all describe different actions, they're all symmetries of the strip pattern. And then you can classify strip patterns. So I'm going to use what is called Conway's description. John Conway was a mathematician. You can look him up. So he used these footsteps. So you can literally walk this strip pattern or dance this strip pattern. So there are only 7 types of strip patterns. The first one, it's called a hop. So you're basically going, I can't quite demonstrate it, I'll probably fall. But there are only translations as symmetries. Okay? This one is step. So you go like that. And here there are only translations and glide reflections in this strip pattern. And this one's a bit difficult to do. It's called a sidle. So you go this way, this way, this way, this way. And here you have translations, of course. And then there are vertical reflections possible. So only the things mentioned are the only ones that are possible. The others are not possible. Okay, and then you have, so we had the hop, step, sidle, and now we have spinning. So you're going this way, and so on. So he's got really nice names. And then spinning, sidle. So you spin and you sidle. And then you have a jump. And finally, you have a spinning jump. Okay, so can you imagine? I mean, these are you draw any strip pattern you like, it'll fall into one of these 7. And then, of course, you can group theoretically study the groups. I've only told you these are the types of symmetries in that. I haven't told you anything else about the structure of the group. So you can also study that. Okay? And then we come to wallpaper patterns. So it's basically a strip pattern which is repeated at equal intervals vertically. That's how you can think of a wallpaper pattern. But it turns out that if you want to try and classify wallpaper patterns or try and study them in a systematic way, you have to think about the underlying lattice. So it's like what regular figures that you can draw to cover the entire plane. And it turns, that's basically what your lattice is. And this is a wallpaper pattern which has been made using what is called a rectangular non-square lattice, which means that the distance between two motifs horizontally and the distance between them vertically are not equal. That's all that's happened here. So you make your rectangular grid, and then at the point where the intersections are happening, so you make a rectangular grid like this, and you place your motif in these places and do that throughout, and that's one type of wallpaper pattern that you can get. You can also get one using equilateral triangles as your grid, or hexagonal lattice, or square lattice, or parallelogram lattice. These are the only 5 lattice structures that you can make on which you can base your wallpaper patterns. But you had 7 types of strip patterns. There are 17 types of wallpaper patterns. And classifying them becomes a lot more difficult. Okay, but again, it's been done, it's well known, and you can look it up. And now I just want to briefly talk about Escher. So this is MC Escher, this is a self-portrait. And can you see this thing here? It reminds you of the Mobius strip. Yes, it's based on the Mobius strip. So how many of you have heard of the Mobius strip? Okay. For those of you who have not heard of it, take just a rectangular longish piece of paper, and if I join it like this, what will I get? I'll get a cylindrical thing. Now what you do is, instead of joining it like this, you twist and then join. And what you get is a Mobius strip. And if you're an ant and you're traveling on the strip, if you were in a cylindrical thing, there's an inside and an outside, right? But in a Mobius strip, there's no inside and outside. And if you actually do this and you take a pencil and draw a line, you'll see you'll come back and join it where you started out with. So it's a one-sided thing. So this has been inspired by the Mobius strip. This is one of his artworks. And I'm just going to keep quiet and show you his stuff. This is the butterflies that I showed you. Okay, this one. So do you see golden or do you see black? Or you see both? But you see, when you see golden, look at the black. That's also, but it's facing in the other direction. Right? So he does things like this. It's just amazing. And I mean, I've not even touched the sort of surface of what he's done. You just go to his website, I'll give you the reference later. It's just amazing things. Okay. He calls this metamorphosis, I think. So there's fish, or maybe I'm not sure what he calls it, but there's fish and there are birds. This thing. This is metamorphosis. So you're starting out with a fish, and then you become a bird. Okay? This one, actually there are lots of animals and birds hidden in this thing. And the last thing that I've put here, this is coming out of an equilateral triangle, basically, in a sense. These are coming out of hexagons. So if you can see this pattern of these 6 dots. Yeah, can you see these 6 dots here? It's nothing but a hexagon. So he's basically taken a hexagon and then moved it around and used it to create that. Okay? So how do you study art using a lens of symmetry? Okay? So you could study something like this as a wallpaper pattern, try and see what are the symmetries in it. It also will give you an idea of how it was created. And then you can create your own things through that. If you want to study something like this part inside looks literally like it's almost fractalish in its kind of thing. So often what we do when we study nature, we have to ignore some things. Otherwise, we can't really study. So suppose I'm looking at the Taj Mahal, for example. I have a photograph of the Taj Mahal with the canal. There are trees growing on the side. And if I say there's a reflection symmetry there, I have to ignore the trees because they're not going to grow at the same heights all the time, right? So therefore, when you try to apply the lens of symmetry to study things in nature, you have to allow for nature doing random things as well. Okay, so even flowers, but typically you'll realize that maths actually plays a very big. So, for example, beehive. Why are they hexagons? Why? Who taught the bee to make its hives so that they're hexagons? Why didn't it choose a square or a rectangle or a circle? Go and search. You'll find that there's something amazing about hexagons because of which this is happening. And a lot of it has to do because it needs efficiency in terms of storage of honey and various other things. So a lot of things in nature are coming out because there's the skeletal structure is mathematical there. Okay. So anyway, I'll just give you one demonstration of what you can do with Escher. So I've actually rotated it. You can make out I've rotated it because the square outside has changed. But if you look at the actual figure, looks exactly the same, right? And this thing is like a Mobius strip version with three things. Yeah. So what it's done is, no reflections will work here. Again, this will have only 3 rotations. Okay? The other things that I showed you can look at them as strip patterns if you want. Some of them you can look as wallpaper patterns and then try and study them. But I want to move on to other things I want to tell you. So I'm going to kind of cut short the symmetry thing here. But one last thing, there's this lovely book by Marcus du Sautoy, it's called Symmetry, A Journey into Patterns of Nature. And it's written as a month-wise exploration of things, and he and his son are exploring, basically. And the main focus is the Alhambra Palace, which is where you're supposed to be able to find jalis, which are exhibiting all the 17 wallpaper patterns possible. So he's going and searching for them. So it's a lovely book, but he's a mathematician, he does research, and so this is what he's kind of saying. So symmetry is one of these things where you can talk to school students about it. You can get very mathematical and get into, group theory in a big way. And then this kind of a thing, he's actually raising research questions in a popular book. At least you can understand what these questions are about. So he says, what different mathematical objects are there which have 3 to the power 5 symmetries? So that is, he's asking, are there objects whose group of symmetries has size 3 to the power 5? Yeah? Such an object has symmetries which are sort of built through the symmetries of 5 triangles, he's saying. If I change triangles to pentagons and heptagons, there are infinitely many primes and hence infinitely many prime-sided building blocks. What is the nature of all the different shapes that I can construct whose symmetries are built from copies of one prime-sided shape? Okay. Or this kind of a question that he comes up with, which is you choose any prime number and how many different objects are there whose group of symmetries will have size p to the power 5. Does it change if I change the prime? So if you count the number of objects whose group of symmetries has size p to the power 5, if I change p from 2 to 3, 3 to 5, 5 to 7, 7 to 11, will it make a difference to the numbers? Is it dependent on p, or is it dependent on the fact that I've taken 5 copies? Lots of things to think about, right? So that's basically what he says. And these are the things for, so if you look up Punya Sharma, he does a lot of lovely ambigrams. And that's the book that I was talking about, Marcus's book. Now, obviously, the rest of the things are going to be pretty quick. So this is radon, and there's something called the radon transform, which came up in 1917, and the CT scan was invented around 1970. So something from what you would call pure maths result. Basically, the idea is very simple, that suppose you know the value of a function around on its boundary. Can you reconstruct it inside? Okay, and that's pretty much what radon worked on. And now it has applications in whatever this computed tomography or CT, CAT scan, X-ray, the X-rays that you go through when you do airport security, in geophysics, and so on. All of this is coming from here. So let me tell you briefly about it. So this is just an image of a CT scan. Basically, rays are sent, suppose that's the brain they're examining. This thing will keep rotating and send beams which cut through so these are single points, single lines you can think, which are crisscrossing through your brain, okay? All around, it's going through. Now the point is, it enters from one point and will come out at one point. In between, there's bone, there's tissue, there's blood vessels, there are things of different densities, right? So the intensity with which the beam goes in, you'll know that. Intensity with which it comes out, you'll know. Somehow you have to build what is the different material through which it is passing through inside. Okay? So, I mean, I've already explained to you what really happens when you're doing it. So the main thing is, what you're really measuring is only the loss of intensity. Okay? And using that, somehow you want to create what's happening inside the brain. How do you do it? So in a sense, you know the value of the function, the change in intensity, only on the boundary. And that too, you don't know it fully. You only, because you can't send infinitely many such lines, right? It's not possible. You're only sending finitely many. Through that, you have some values on the boundary, and then you want to be able to reconstruct what is happening inside using that. So how do you do it? So let me take you through this. So the X-ray, there's an initial intensity and a final intensity. So the initial intensity I'll call I0, and the final intensity I1. Okay. And basically, when the X-ray goes through, there's a proportion of photons absorbed per millimeter of the substance at the distance x from the origin. And the proportion that is absorbed, that's called the attenuation coefficient. We'll call it AX. And this is the mathematical equation which governs it. All right. And what you know is this. This is log natural. So you know I0 by I1, and you have to get AX back. But it's not as simple as just differentiating on both sides or whatever. It's much more complicated because there are different lines going through, and this is a three-dimensional structure that we are trying to recreate. So the next page is the maximum maths, I promise. Okay, we'll just go through it. I've put as little as I can. So basically, where does radon transform come in? So you have a function of two variables. Basically, that means that on a surface, so take like a piece of paper or my hand, for every point here, there's a value for the function. So you can think of the function as a lid over this hand in a sense. So that's what your f t theta is. Okay? Then there is something called the radon transform of f, which is denoted by r f t theta. And in this, basically, you're parametrizing t and theta via a line, points on the line, which is your s, and integrating it, and you get the value for this thing, okay? Where your xs is t cos theta, s sin theta, don't worry about it. So for every function of this sort, there are some conditions on the function. I've not put it here. There is what is called its radon transform, okay? And what is happening in a CT scan is that this value that we calculate, it's like finding the radon transform of the function. What is the function whose radon transform we are finding? It's A of x. Okay. And so once you know the radon transform of a function, you can get the function back. That's basically what is happening. And of course, there's a lot of real analysis going on here. There's something, Fourier transforms are used for something called the Fourier central slice theorem and the inversion formula. All this is required to be able to get back. Yeah. So that's what happens when you are doing this thing. So it's the idea that you know a transform of the function, which is essentially like values on the boundaries, and you're able to get the function back, you're able to reconstruct it. This was the theory on which CT scans were based. And of course, they used, so there was this mummy which they wanted to investigate. They can't cut it up. So they did a CT scan on it. And the last thing that I want to tell you about is cryptography. I mean, all of you have probably experienced sending secret messages when you were in school and so on. Very quickly, so plain text is the message you want to send. Then you convert it after encryption. Encryption is the method by which you convert. Decryption is the method by which you get back the original method. And this is like the schema. Okay, so the algorithm is well known usually. So you have the plain text. Think of this like a box. The plain text goes in. There's something called the encryption key, which is used, which is specific to that particular time when you're doing it. The algorithm is fixed. It's like a fixed box. Plain text will change every time you put it. The key, there's something called the key by which you encrypt, and what comes out is your cipher text. And when you want to decrypt, again, it's the kind of opposite thing that happens. Now, the point is the key, the encryption key and the decryption key are what are governing the actual encryption and this thing. It's like your key to lock and you're using the same key to open the lock, right? So in cryptography also, there's a key by which you encrypt and there's a key by which you decrypt, and they're very closely linked. And the robustness and efficiency of the system are because of these two keys. Now the problem is, suppose I want to send you a message, right? I have my encryption key. But if you have to decrypt it, you need the decryption key. I have to give you the decryption key. But that's a secret thing. If I was anyway going to meet you, I'll tell you the message also to you only. No? So it's like a chicken and egg situation. Either I should have met some 50 years ago and exchanged one decryption key with her. Otherwise, what do I do? How do I do it? And maths has an answer. These are called symmetric keys, by the way. That is, these two keys are closely linked. You know one, you know the other. So they're called symmetric keys. There's a physical analog of this problem. Okay? So imagine you're in a country where valuable items can only be sent in a box, which you know, like you lock your house and then you put a lock, that kind of lock you can put. That's the only way. And it's a rule-abiding country where people don't break boxes. Okay. So I want to send her a very valuable thing. She's somewhere in the country, not sitting in front of me. So I sent her this box. She can't break the box. She doesn't have the key to the lock. What will she do? So think about it. And in the meantime, I'll tell you what happens mathematically. Very quickly. Okay, so in 1976, Diffie and Hellman came up with a wonderful paper, which sort of sets up things for what is also called asymmetric key cryptography, public key cryptography. I'm not doing that in this talk, but they came up with what is called a key exchange. There was a way in which people don't have to meet, but they can come up with a common key. And you use maths to do it. So, and you need groups for it, but I'm not telling you this in terms of group theory. Okay, let's just see what this is. So this is the given to you that every number n. Achha, by the way, the plain text and all are usually converted to numbers. Everything works with numbers rather than letters of the alphabet. You can use your ASCII code to convert every keystroke into a number, and that's how it functions. Okay? So think of every number, this is what is given to you. So there's a base G, and every number n can be written as G to the power A for some A. Okay? And the A will, of course, depend on the n you choose. G is fixed. Now, this reminds you of log and exponents, right? You can, if this were a log, if I told you that n is e to the power x, then you would say take log on both sides, and x is nothing but log n to the base e. But unfortunately, these are what are called discrete systems. Okay, everything is like finite. It's not a continuous function that's in our, oops, sorry. Okay, so the problem is in these systems, even if you know n and g, so they're public, you can't calculate the a. It takes too much computer time to find this a. This is called the discrete log problem. Okay, so you know the base, you know that n is going to be g to the power a, but you can't compute a. That is given to you. All this is given to you. So how do you use this to create an exchange? This is what you do. And in cryptography, usually you call the people who are doing these things Alice and Bob. So say Alice wants to send Bob a message. So what happens? She chooses this little a, which is secret, and she calculates capital A, which is G to the power A. Then Bob does the same thing. He keeps B a secret and calculates G to the power B. And these are put out publicly. This G to the capital A and capital B, everybody knows. Okay. Now I know capital A, I know little g, but I can't find little a because discrete log problem. I can't find little b, same issue. Okay. So what does A do now? Alice do now? She knows B now because it's been put out publicly. And she has a little a which is secret. Right? So she does B to the power A. What will she get? G to the power BA. But this is in the commutative scenario. This thing is the same as G to the power AB, which Bob can calculate because Bob can do A to the power B. So both of them find this capital K, which is the common key. So they've exchanged their keys. Right? This is called the key exchange method. All this is in a mathematical setting, which I've left out. Anybody who's eavesdropping can't find K because to do that, they have to solve the discrete log problem. Okay. So have you solved the physical problem? The locked box? Anyone? Okay, here's a hint for it. I'm not telling you the answer. Have you got it now? Yeah, so what she does is, she'll put a lock and send it back to me. I remove my lock and send it back to her. And she opens her lock. Okay, so it's the analog of your key exchange. And the very last slide, so this, I want to tell you about Ingrid Dubashi. She was the first woman president of the International Mathematical Union, which is a union of all, it's a big thing which does all the maths activities in the world. And the Fields medals, which the previous speaker also mentioned, which are tougher to get than Nobel Prize because you have to be under 40 to get it. And you should have done some fantastic work. And every 4 years, at most 4 are awarded at the International Congress of Mathematicians. She was the first woman president, works on wavelets. And you know, every time you take a photograph with your phone, there's JPEG in which it is saved. She invented JPEG, Ingrid Dubashi. And her work, interestingly, has been used to track art restoration. It's really nice. Just look her up, you'll find that. But the main reason why I want to talk about her is, I heard her say we should all have a sticker which says mathematics inside, and you put it on anything that can be studied using mathematics or described using mathematics. All of us would be covered with these stickers. Every single thing here would be covered with these stickers. That's how useful and beautiful mathematics is, and I hope I've conveyed this to you. Thank you.
Thank you, ma'am, for the wonderful talk. Do we have any questions? Please feel to ask any questions.
Don't be shy. And there are no bad questions.
Isn't that glide reflection thing?
Yeah.
Just translation and then reflection.
See, so the problem is that when you look at this, I told you that when you're looking at a finite figure, planar figure, which means you can draw a rectangular box around it on a plane, then there are only reflections and rotations possible. Okay, but when you look at the plane as a whole, right? So I can draw a line on the plane, reflect the plane about that line. I can take, say, the origin, any angle, rotate the plane, it will still look like the plane. I can translate the plane. Okay. So these are the things we can think of naturally, right? So then we make the group, the collection of symmetries. We know that a symmetry followed by a symmetry has to be a symmetry. A problem arises when you try a translation followed by a reflection or a reflection followed by a translation. It doesn't come back to these three. So then you have to figure out how to describe something like that. So if I take a R, say, and I reflect it about this line, okay? I'm not sure, I should be drawing this. It'll be something like this, okay? Then I say translate it like this. Okay, so I've done a reflection followed by a translation. So this was the starting position of the R. This is the final position which has come if I've done it correctly. Now, can you describe this through either a translation or just a single reflection or just a rotation? You can't, right? So then they figured out that there is another kind of symmetry which is possible on a plane, and instead you do something. So if this is the final figure I want, so what I do is I kind of like reflect here and then translate. So this is called the glide reflection because what I did earlier, the line of reflection and the translation were not parallel to each other. But the net effect of it can be described by doing what is called a glide reflection, in which the line of reflection and the translation are parallel to each other, and that's called a glide reflection. So the reflection and the glide reflection are what are called orientation reversing things. Like the R becomes an ulta R. So whereas a rotation and translation are orientation preserving things. So that's how the glide reflection comes up. But these four, so if you take the collection, so imagine how large the collection of symmetries of a plane would be. Right? Any line you reflect, that's a reflection. Any point you pick, rotate by some angle about it, that's your rotation of the plane. Any vector, translate the thing, and then you have glide reflections. So how do you understand that you have such a huge number, right? And that's where group theory plays a role, and there's a wonderful structure something like this has. You can break it up into small groups, which then put together gives you this large group, and you can say that every single thing in this will look like this. So that's how group theory plays an important role. These things are called motions, and then so there's a motion group, which you can then describe. Okay, so I have one exercise for all of you. When you're walking on the road, you'll see the pavement has some interesting tiling. Yeah? Or sari borders. Okay, here. This is a strip pattern. Yeah? So what would be nice is just look for objects around you, cushion covers, carpets, curtains, patterns on fabric. Okay? And there'll all be examples of strip patterns or wallpaper patterns or even finite motifs. Just start looking at them with the lens of symmetry. And remember, you know that if there are only finitely many symmetries, equal number of reflections and rotations, or just rotations. So it'll be fascinating to examine your surroundings just using symmetry. Anything else anyone wants to ask? Otherwise, yeah, there. Someone there?
I think we can discuss it after the talk from 6 to 6:30.
I'm outside. We can chat. No issues.
Both the speakers are there for the interaction in the foyer from 6 to 6:30. Let's thank again our speaker for this wonderful talk.
Thank you.